Hello, everyone. Welcome to today's webinar on better understanding RoadEng. This is Erin, one of the resident webinar hosts here at Softree, and we have an absolutely action-packed 30 minutes of content, which I'll be really honest is probably more like 45. So let's kind of get right into it. So today we are focusing on some key elements of the modeling system that RoadEng is built upon to help you better understand it and then to be able to implement some of the concepts and ideas that we've got in it within your own designs. So we're really talking about sort of 6 key areas of the software's foundations. First of which is going to be sort of terrain models and the terrain model requirements that you need in order to build your RoadEng project, I should say. Next, we're going to talk about the cross-section model that the software is built upon, the idea of report points, what they do, how they're used, and the very, very important role they play in the software's volume and cross-section calculations. And from there, we'll talk about sort of 3 volume-related topics: the average end area model that we used, expansion and compaction factors and how those apply, and then the mass haul and Opti haul graphics and volume reporting methods, and some of the limitations of the mass haul and why you might want to use the Opti haul. For those of you that are totally new to RoadEng, though, we're going to have a little bit of fun here because, why not add more content into a 30-minute webinar? We are going to do a speed road design under 5 minutes just to add some context. So for that, I am going to pass it over to my co-presenter today, which is Matt, our training manager, and he is going to load up the software and go front to back design in under 5 minutes. Matt, are you there? And if you're talking, Matt, no one can hear you. I think you're muted.
Just saying when no one could hear me there, this probably won't be super valuable for those of you that are longtime users of the software, this kind of overview, but we do have some new folks in the audience. So I'm starting out in Train. I'm going to click Insert File. I'm going to grab my topo surface. I'm going to just dump that in really quickly. Series of points and lines. We're going to turn that into a tin. We're going to save. We'll call this topo. Then we're going to jump over into location to do our actual geometric design.
And that's the 1 minute mark, Matt?
The pressure on. I think I should be good. And I will be focusing on just the gist of it rather than hitting this out of the park, but I still think we've got lots of time. All right, so I'm going to start in the plan view. I'm going to just move my first IP to where I'd like the road to start. I'm going to click in my IPs. And I guess as I kind of do the boring stuff here, the whole premise of this, once we get into the content, is to talk about why things work the way they are and what's happening in the background this whole time where I'm clicking around and making a road. So we've got that. We'll throw in, so down here we've got our mass haul. We'll be talking a bunch about that here later. And we'll try and get close to balancing. I'll throw some vertical curves in there. So very close to balancing. I've got my 3D so we can see this surface that we're working with and looking at. So I've figured out a road design. I would have, if it was real, not just rushing through it, I'd spend a little bit more time on the details, but that is the gist of it. So I'll send it back to Erin and we'll continue along with the stuff everyone came here for.
Awesome. Well, that just let you know, that was 2 minutes and 45 seconds. So I'm impressed. Perfect. So next up, we're gonna now start too with that really high level introduction and context. We're going to start talking about these different foundational concepts. So we took a quick look what the software is doing, how it designs the road, well, why does it do it that way, and what are the elements that control it. So the first step that Matt showed us in that brief introduction was the creation of a tin surface or a terrain model. So just a quick explanation for what that is. As you see here, same project that he had loaded up. These are our survey points. And right now, this is just with the data imported. We don't have a surface, and you can actually see that here, because in a 3D model, you would typically, if you're using default settings, see that 3D surface. So this by itself is not enough to base our road design on, because we don't have a complete surface. We just have points. So Matt went up, used our terrain calculation dialog, and he was able to generate something called a TIN. A TIN stands for a triangular irregular network, and this connects the points with different triangles. These triangles then can form a full surface. This view that you see here is not typically shown. However, you can enable it pretty much at any time if you wanted to see how your TIN's being created. And our sort of more typical view of what the surface looks like is this one here, where you have that sort of 3D surface. You can sort of see the shading of the 3D facets, or triangles, I should say. And that's a base requirement in order to be able to go and do your road design. So we need that surface. A quick note, not all tin surfaces are the same resolution. And it's just our software is going to be able to design a road on any of these, but this really comes down to being an engineering decision if you are comfortable with the vertical and horizontal density and accuracy, or quality, I should say, of your surface. So obviously on the left, much lower resolution data. This is the SRTM data set. And then on the right, we've got some high resolution LiDAR. So RoadEng can work with any of these, but again, it comes down to you as an engineer, whether you are comfortable with the quality of your tin surface that you're basing your road design on. Okay, so from here, we're gonna go in and for the next minute or two, just talk a little bit more detail in the software about these terrain modeling requirements.
Cool. So this one, I'm not going to go into a ton of detail. We've done previous webinars on terrain modeling, and we'll send the link out with the recording for that. But just at a high level, we're going to talk about that tin surface and maybe touch on some things that are limitations or approximations that come with that. So I'm back in terrain. I'm going to do that same thing that I did in the previous step. I'm going to bring in that conventional survey data to start. So here and in our other content, this is our IOP, which controls how things are brought in and matches the format we'd like. And I'm stuck with a series of points and lines. Now it's all 3D data. And if I want to, I can calculate a tin from it. So that's the surface that we're left with. Now we can do things like control where triangle edges are allowed to be and not allowed to be with the use of break lines. But we can see these triangles. I think and it's obvious, but it needs to be said that, well, we're only dealing with the information that we have. So if there was something, and I'm gonna just turn on my triangle surface here. If there was some important point that landed right here where we don't have data, we're not modeling it or accounting for it. So it's going to be just a representation of what we have. Next thing to note is the interpolation between these points. We're using just a straight line. So if it's something that would have been better represented by a curve or some weird interpolation that isn't just a tin, and now tins are pretty standard in the industry. So it is what it is, but it's the model that we're working with. no more, no less. And then the other thing is, if any of this information is just bad data, well, we're still modeling it. So it's up to the designer to recognize, oh, this is a bad point, or the surveyor, if the surveyor is collecting the survey data. So if this point had a bad rod height in it when it was entered, well, the elevation at that point and within the triangles that touch it are going to be wrong. This is a conventional survey data set. So of course, with that, someone actually chose where each one of those points is being located. With that, you get some sparser data, but it's the location of those surveyed points is more deliberate. Now you can have something that's a little different. Actually, I'm going to turn this off before I do it. So the other common data type is data that is brought in from either LiDAR, drone, or remote sense formats. So the same surface, if we use a DEM for it, and I'm going to just model this. So this uses that point cloud data. We can see we've got a much higher density of points, but we're kind of at the mercy for the sensor to make sure it shot spots that were reasonable to capture. Yeah, and just to reiterate, if you want more information about terrain modeling, we recently did a pretty decent webinar and have the recording up on our YouTube page that we'll link to. So back to you, Erin.
Okay, so let's move into our next concept, which is really about talking about the cross-section model that the software is based on. So as Matt just showed, we start with a tin surface. To that tin surface, we add a center line, and if you can see here, I don't know if you can see my mouse, but I am wiggling over it. Down here in the bottom, we've got kind of a crossing line over top of our center line. And this is where this particular example of a cross-section is being pulled from. So we have a cross-section model that is attached to the center line and defined by its station range. So you can assign multiple different cross-sections by station ranges along the center line. And it's going to interact with the surface and that center line, and a concept that we're going to talk about in a whole lot more detail called report points, represented here by the purple balls, to create the surface, the designed surface of your road. This cross-section model is essentially like a mini program. It adapts and changes based on your topography, based on the materials it's sitting on. So in this screenshot I've got here, we've got a couple different subsurface horizons. And if you look really closely, you can actually see that the cut slope is changing depending on the material in the different subsurface horizon. Similarly, the fill slope will adjust as well, and the entire cross-section, whether the presence of ditches or berms, can adjust depending on whether you are in cut or fill situations and the height of those particular elements. So these little mini programs, you can have lots of them in your design, and they are assigned to that center line for a specific station range, with, of course, the ability to add tapers between those different elements. We've got a whole bunch more resources. Again, we're going to include these links in our follow-up email and up on our YouTube channel, but lots more resources that go into a huge amount of detail on cross-section templates, how to work with them, and what they are. But for today, we'll do a quick little discussion of how this cross-section model works. And for that, I'm going to pass it back to Matt.
Alrighty. So as Erin said, we've got a bunch of resources on this. We could spend an hour on just cross-section geometry and hardly scratch the surface. That being said, pretty simple concept. We've got, well, those report points that dictate where we're generating our cross-sections. And well, here I've got my ditch, whereas if I go out here, I don't have a ditch. So these cross-section templates get assigned by range. So we assign different templates from station to station. I'm just using one throughout. And they really are like little mini programs. So we can pull this around and we can see how it's going to interact in different circumstances. Now with this, if I pull this way down here, we'll just unpack a little bit of it. So I've got my cut slope set to auto, so it'll recognize the material that we're going through and change the cut slope angle depending on what we have assigned. Or we could just go with a fixed value if we'd like. Now, similarly, here I've got a ditch, whereas if I'm in enough of a fill to not need a ditch, it eliminates it. So there's logic baked into these. And then as we talk about it here later on, these cross sections are really the backbone of so much of our software. It's well, going to be directly what dictates your volumes that are being calculated, and also dictate all of that geometry beyond just the center line. So as we go out from the center line, we're getting our road edge points, the slope stake points, all relative to this little mini program that is our cross-section templates. Another thing worth mentioning before I forget, and for those of you that have seen me talk on here before, probably notice a lot of the time I've got hatching turned on in my cross-section view. And that is, well, it does two things. One, if I right-click here, I can toggle it on and off and just see what's being tracked as SG. So SG is being subgrade, so that's my subgrade fill. Or if I pull that down, I can see it's being tracked as my cut. By having that hatching on, it makes it a little more obvious if I went into the guts of this and created something entirely new and introduced undesirable behavior. It makes it a little easier to see what's going on and identify issues. And then the other thing is we're not just looking at our subgrade. So all of these other materials, we can hatch them separately. So that's being hatched as SRF1, SRF2, etc. So it's yeah, just a very high level introduction to templates. Recommend folks, if you have any interest in it, to check out some of our other content that Erin introduced. And back to you, Erin.
Okay. Hopefully you guys are all enjoying all this screen flipping we're doing. So our next topic that we're going to chat about, I'm going to say is the most important of the entire presentation. So if you are checking your email or doing something else on another screen, this is the moment to pay attention to. Probably one of the most misunderstood concepts in this offer, and this is report points. So report points, and they're, as I mentioned before, these are the little purple dots here on our, or the lines, I should say also. You can see where they are. And report points are basically cross-section calculation points. They help us to make sure we've got reasonable volumes and a reasonable representation of site geometry. And they come in a whole bunch of different categories and types. The most common ones that I'll just quickly introduce them here. We've got our standard editable report point. That's one that you can add yourself at any point in your design. Yeah, you can right click and add it, and Matt will demonstrate that in a few moments. If you're working with a P-line traverse, there is a report point that is being brought in and calculated at every station you collect, of data you collect. We have auto interval points that you can define. There's two different ones. You can also turn them off if you don't want them. But those auto interval points are going to be creating those report points throughout the length of your project at those specific intervals. If you put in a culvert and a report point gets created, and the other really common one obviously is curves. So as you put in curves, there are report points that are automatically created for those as well. Now, report points are a bit of a balancing act. So the more report points that you have, the more accurate your volume calculations are going to be. But of course, there is going to be a point of diminishing return where too many report points are not going to increase the accuracy of your volume calculations, and they're going to slow the program down. Basically, the more report points you add, the longer, in a sense, you are making your road project. So let's talk about the two extreme examples here. So our first example is a switchback. As you can see in the screen capture here, especially through some of these curves, there are not enough report points. We are not getting a very accurate visual representation of what should be happening through those curves. If we were to increase the number of report points, let's just pay attention to this one section here. I don't think you can see my mouse, but if you could, if you right there, you can see that with more report points, again, represented by those lines in the 3D window, we get a much more accurate looking model of what our curves are doing. On the other side of this, I'd say equation or scale, is what happens when you add too many report points. So on the left, the cross section is almost, or I should say the 3D view is almost black because it has so many report points. And being in a relatively benign topography, these report points are not increasing the accuracy of our volume calculations by very much, and they're really just slowing down the software. So in this case, you know, something like a more on the right, a more reasonable, larger spacing of report points is still going to lead to very accurate volume calculations, but your software is going to be much, much, much faster. So with that, back to Matt. Let's take a look at how this plays out in the software.
All right, and just while I switch over my screen, yeah, and just to reiterate that idea of performance, if you double the report points in your model, you're basically doubling the length of your road if all else is held equal. So yeah, you go from having a 40-kilometer road to a 50-kilometer, or sorry, an 80-kilometer road. Well, they're introducing some lag. But too little report points or too few report points, and it isn't good either. So in this example that we were looking at when Aaron had it up, that we've got this kind of worst spot is in here. So we can see that the actual center line, the alignment, is proper. We have our alignments in alignment, so being a combination of straight lines and curves. But through here, we have our road edge even cross over center line. So that's weird. Now, if we want, we could just add in a single report point in that stretch. So Aaron introduced it. I'll show one location where we can see it. So report points, we've got standard editable report points. And right now I've got just a tick set as my default symbol. So if I go in here and I click Add Edit Report Point tool, I'm going to drop that in right here, and we can see we've got a tick to indicate that's where we've added that standard editable report point. Now we can do that elsewhere. I can hit delete and I can remove those ones I've added. Usually you wouldn't be doing standard editable report points dropped in by hand to capture this. This is a product of we're just not sampling enough. So we'll come in here. Now I'm going to just change this to be, so auto interval point, we'll set that at 5. And there we are, we get this much smoother line work. We've also got a much better representation of where our toe of fill and top of cut's going to be. And we're sampling more often, which is going to give us those better volume estimates as we talk about volumes here in a moment. These report points, well, they're obviously useful for line work and volumes, but they're also used throughout the software for other things, like influencing when certain things are being reported. I'm going to fire up a quick data table, and of course I've got that landing off my screen somewhere. So I've got a data table here. I'm going to configure it, and I'm going to just set up my columns to be something that is, well, a common thing to report. So we'll go station and our cut and fill volumes. So there we are. Now, point types, if I keep that at all, we can see we're getting every one of those cross-section points is showing us the information associated with it. That's probably, it might be good if I'm looking for, oh, why is that the way it is, and looking at specific sections. But if I want to get a glance of what's going on with my road, that's too granular. So I'll come in here and I'll change it. So I'm not interested in everything. I want to just see, well, let's summarize this in 100-meter intervals instead. So I've got another class of auto interval points. And there we are. So now 0, 100, et cetera, And it'll be an odd number at the end just because it captures whatever the end station is. So useful in data tables, well, useful to get good line work and reasonable volumes. Good for setting up what's being reported. And then outside of this, it's also used in like the multi-plot or setting custom labels to certain points as well. An example in the multi-plot, if you wanted to just produce cross sections where you've got culverts, well, you would set that up to refer to your culvert insertion points. So with that, I'll send it back to Aaron and we'll continue along.
Perfect. So our next topic really starts to dive a little bit deeper into volumes, and this is how volumes are calculated within RoadEng. So the location module uses an average end area calculation, which essentially means that it's calculating cross-sectional areas applied to a specific length. Now that length is defined by the presence of report points. So obviously, as we mentioned, the more report points you have, the more accurate your volumes are going to be. And that's because it's calculating more cross sections. Again, remember, point of diminishing return, though, you have to find a balance point for performance in your computer. And those, again, are engineering decisions that you get to make. So report points are going to dictate where these cross-section calculations happen. Yeah, and it's a very, very important calculation that's happening within the software. And that was the shortest intro to a topic. Matt, back to you.
Perfect. So I am going to do something a little different here. And we're going to use this for the rest of our chat, just where we're going to get into, dive down the rabbit hole and get into some stuff that's a little, can be abstract. So with that, one thing I think that's worth just mentioning or acknowledging is as we get into more complex stuff, sometimes it becomes hard to understand it with complex examples. So here, you'll notice that my topo surface is as boring as it can be. So I've got a planar slope that my road's going in a straight line. My cross-section geometry is as simple as it can be. So for me, if I'm going to step through volume calcs and make sure things make sense, I don't want to worry about the logic of adding ditches and not and having to make sure, oh, there's a ditch there. Here we've got our cross-section geometry that has the same cut and fill slope. It's a symmetrical road, no surfacing stuff that we need to worry about, not even a crown. And yeah, we'll roll with that. So at station 100 here that we're looking at, we could use the measure tool and measure out our cross-sectional areas. We don't have to. I've also got it shown as a field. So I've got my cross-sectional areas called out for my cut and called out for my fill. So with that, I can see at this station, I've got 9.7 square meters of cut, and I've got 9.7 square meters of fill. And just to make this really palatable and intuitive, right now I've stripped out any fill factors that I'm applying. So my cuts and fills here, my fill factor set at 1, and I'm leaving that for all my materials to start. So 9.7 cut, 9.7 fill. If we look at our mass haul diagram, which we'll talk about momentarily, it's running along at 0. And if we pop open a data table, I've got my report points set at 10-meter intervals with no other extra stuff that makes warrant an additional sample. But there's a little bit of rounding, so that's probably 9.69 instead. So between station 90 and 100, I've got 96.9 cubic meters of cut and 96.9 cubic meters of fill. Just while we're on the topic, a fun note, that stuff that's measured between stations is reported between the station lines in our data tables. So that is cross-section model in a nutshell. Send it
Okay, back to me. Awesome. So let's keep talking about volumes and continue to sort of build the model background that we're sitting on. So as Matt mentioned, we're going to talk a little bit about the mass haul. We're going to do this in a couple pieces. So to start, the mass haul, as you can see here, it's a reporting method for volumes along the length of our road. So this is chainage running this way, and this is just a material balance. So as we start here on the left side with a cross section where we're predominantly in cut. So when we're more in cut, the mass haul rises, we're creating surplus. And moving into the middle cross section, as we have more fill, the mass haul is falling and we're creating a material deficit. And here on the end, as Matt was showing inside of his initial example, as we have a sort of balanced or equal cross section, we have a flat mass haul. Now, these volume calculations that are being done for these different areas and volumes have another layer of detail that we need to add to it, which is the fact that as you change and extract material and place that material, we're going to have expansion and shrinkage, or swell and shrinkage. So these vary by material type, and there's essentially 3 different states, and each material is going to behave differently in these states. And we need to be able to account for these changes in volumes by materials. So the first state is what we call banked volume, and this is really the volume of natural in-place materials. As we excavate it, it becomes loose material, and it does typically, for most material types, we're going to see some swell. It could also contract, which is shrinking. And then once we place it, the final state, we're going to have a different volume here. So we need to be able to account for these different volume changes for the material as it moves through the 3 different states. So to add that next level of detail as a part of the RoadEng model, I will pass it back to Matt.
So there we are. Same planar slope. And I'm going to do one thing here to start. I guess I should have had that set. Oh, darn. You guys are going to get a sneak peek of where I'm going with things before I
I'll take this opportunity while you fix your model to say that if you joined us late, we're going over time. We knew it in advance. I think the webinar clocks in about 45 minutes. So hopefully you can keep joining us. And then my standard housekeeping, which I skipped. If you have questions, we will hang out even longer in this webinar. So feel free to type some questions into that question section of the GoToWebinar panel. We'll tackle all those at the end, and question askers do remain anonymous. Okay, Matt, your screen is ready.
Perfect. So the same example Aaron was showing there with the mass haul diagram, where things are balancing, got some fills, our mass haul is flat. Back here where we dip down, it's climbing, and out here where we rise up, it's, well, we're creating a deficit of material. Now this is all dynamic, so if I were to increase the fill even more, we can see, well, now we've got this massive deficit of material. So I'm showing up as being 70,000 cubic meters short on this fictional surface. I'll hit undo. So, I mean, the concept is pretty straightforward. If we're creating more cut than we have fill, we'll have a surplus. If we have more fill than we have cut, we'll have a deficit. Usually we try to keep things balanced. So over here, I'd mentioned it before, that 9.7 cut, 9.7 fill. Well, we're going to factor that. So we're going to assume that this material that we're working with is going to shrink. So we're going to go over here. We're going to say, well, fill is now going to be 1.2. So we're going to leave our cut as 1. So we're working in bank cubic meters. And we're going to see changes. So we see kind of 2 things at a glance. One, we're not balancing. We've got a fairly significant deficit on this medium-sized road. So we're at 5K, and we've got a 10,000 cube deficit just by changing that. And then 2, these areas that are being reported are going to be the factored areas. And I clicked the wrong button. Just as a note, if you're interested in any of the explanation for what's what there, if we hit F1, it's going to pop open help for that specific area, and we can see that it's actually making a note here that this is with expansion compaction factors applied. So 9.7, now we've got 11.6 square meters of fill. We're working in bank cubic meters. The whole purpose of that is that 11.6 isn't if we measure this, it's going to give us a different, or the 11.6, it's we factor that back to be in cut. So in order to build that fill as designed, we need 11.6 square meters. Now, if that's true, the opposite should be true. So fill factor 1.2, if we have a material that's going to get bigger, like if we're dealing with rock, so blasting rock, it's going to expand. That factored fill changes from being that 9.7 if it was unfactored to 7.8. And now, same but opposite, we're up around 10,000 cubes of surplus. Now I'm going to set that back just so it's nice and easy. And we will, I guess the last thing to mention here is it does influence not just the volumes, but it influences where you should put the road. So I jumped the gun. We'll put that back to 1.2. Ultimately, if we want to design and have our road balance, we're going to probably consider dropping the grade. And so we end up chasing that balance to get things to equate. I'm going to I won't bore you with the details there as I move that around, but with that, I'll send it back to Aaron and we'll get into the either more boring or more interesting stuff, depending on which group you fall in.
Awesome. So the next concept, I'm going to say this is, we're getting more complicated. And we're going to be talking about the means of calculating that volume balance. So for most softwares, and this is not just a RoadEng thing, the mass haul is the means of calculating volume balance. And if you are using the mass haul without Opti haul volumes that we're going to talk about, that is totally okay. It's the industry standard way of doing it. But we think there's a better way. And so this is, our kind of segue into why you should be doing something differently in your projects. So the mass haul is single material focused. In the mass haul, fill is treated as a single material, and the fill factor that is used is whatever is applied to that material. And it really has one glaring limitation, which is that it doesn't solve for fill composition at different stations. So if you've got multi-materials inside your project, it's not looking at how to handle those multi-materials in situations where you might be using multiple fill types at the same station. So introducing our proprietary solution to this inside of RoadEng, which we think is a heck of a lot smarter, and that's the Opti haul. And this is multi-material volumes and balancing optimization. It solves for what goes where, and this becomes increasingly important as you're working in complicated projects. It's going to acknowledge and account for the fact that a lot of the time fills are composed of multiple materials. And we were going to go into some detail and kind of explain the limitations of the mass haul and why we think the Opti haul is better. And I'm going to actually let Matt do a little bit of chatting inside the presentation.
Alrighty, and down the rabbit hole we go. So yeah, this is certainly on the more technical side of things. But the whole purpose of the mass haul, as stated before, is to figure out what goes where, or approximate what goes where, and to help us identify if we have too much or too little material. For a design with just one material, the mass haul does a great job. And if you have multiple materials with the same fill factor and no requirements for specific materials at specific locations for fill, even then it does an okay job. But it starts to fall apart a bit when we get into stuff like we'll show here in a moment. So in order to calculate that balance and through the lens of a single material, we're going to assign our fill types. So if you have a project that you need a specific section of road to be, say, gravel for your subgrade, so free draining fill, well, then it makes sense to assign a specific material. Most of the time, we're not going to be that selective. Most of the time, we can use common fill or whatever's on hand, provided that it's not garbage. So with a conventional mass haul approach, we're stuck, well, let's guess. Let's say the material is, maybe we make a new material that's called out as being common fill, and we add that for our fill just kind of globally. Or maybe we say we can use whatever's there at that specific cross section. So we can say use the existing layer 1 material as fill or existing layer 2 material as fill. Let's continue along this little thought process on the next slide there. So in this instance, if we set our fill to be existing layer 1 from station to station for the whole road, and we had our first layer of in situ material set as overburden with a fill factor of 1.2, great. We'll set our second layer as being solid rock. So the rock is going to expand, so we've got a fill factor of 0.8 for that. And then we're stuck with just using existing layer 1 as the assigned fill. So just to reiterate, that has a fill factor of 1.2. Now let's put a little bit of numbers to the geometry here. So we'll start kind of through that unfactored lens. So overburden cut, 4.75 cubic meters, solid rock cut, and I'll say cubic meters, just a little more intuitive to talk volumes than something infinitely thin. So solid rock cut, we've got 4.95, and our total cut is 9.7. Now, since we're working in bank cubic meters, we don't have to worry about factoring that. Cut factor is 1. The fill factor, though, unfactored, we've got that same area, 9.7. Or if we treat it as overburden and factor it, we're saying we'd need 11.6 cubic meters of overburden to build that fill as designed. Reality, that's probably not the case. The other extreme would be to assume that it's all rock. So if we apply that 0.8 to that 9.7, we get a requirement of 7.76 cubic meters of rock to build that cut material to build that out of rock. So reality is, unless there's something weird going on, it's probably somewhere between those two numbers. Now with that, if we are okay with it being a mixture of materials, you'll notice we've got replaceable selected in the top there. So approximating multi-materials, down below that, we've got subgrade fill material, existing layer 1, and that checkbox with replaceable quality based. So we are acknowledging that that fill is likely not just one material, but we don't yet know how much of what material it makes sense to dump in there. So next. Figuring out how much of what to put where is, it's not trivial. And we could probably do a reasonable job of guesstimating for that one specific cross section. But then when we add in other portions of our road where we have a surplus of X material or a deficit of another, or something like if we had a rock fill that we needed rock for, we need to know that, well, rock's going there and not just whatever's coming out of the cut slope. So yeah, tracking that material movement by specific material gets inherently complex. It needs to be, yeah, it's just, there's no understating it. It needs to be viewed holistically to get a reasonable number, and the type of problem that we're dealing with is it's an optimization problem. So finding that best solution of an infinite set of solutions, or near infinite set of solutions. So here, if we have something, and this is a more real example than that really simple one we're looking at. If we had something where we had, say, gravel that needed to be used for surfacing, and we had another material used for our subgrade, we can see that at different locations along our road, we're hauling material in different directions. So that's one advantage of the Opti haul. Now, we're not going to dive into that and break down individual sections for that here now. We should be able to kind of illustrate the utility of it, still looking at that simple example that we started out with. So back into the software. All right, so just to kind of recap, picking up where we left off, fill types, just for the sake of looking at it the same as that PowerPoint, we've got existing layer 1 set. My subhorizons, right now I've just got a single material, but we're going to make it more interesting. So overburden over solid rock, 0.6. So we've got two materials. They've currently got the same expansion and compaction factor being assigned. So we're going to say that the overburden is going to shrink. We'll go with fill factor of 1.2. And we're going to say our solid rock is going to expand. We'll hit OK. And the mass haul changes. And the mass haul is just assuming that this is one material, that overburden. We're going to do something different here. We're not looking at the mass haul or the Opti haul diagram, but we're just going to use the Opti haul volumes in our mass haul. We'll hit OK. And we just went from having a deficit to having a significant surplus here, depending on how we're tracking the that devil in the details stuff. And just to reiterate it, mass haul without Opti haul, we've got a deficit of about 10,000 cubes. Mass haul with Opti haul, we've got a surplus of about 3,000 cubes. Now the problem here, or I guess not so much the problem, but yeah, that's great. It's useful, but we're not really getting any indication of the actual composition of what we're dealing with here. If we want to do that, we'll pop up another data table. So this one shows our cuts and fills. So we'll go in here. Now, cuts and fills volume here are coming from this folder. So we've got cut volume, fill volume. That folder is kind of referring to the conventional approach. We're going to break it down in more detail. So we're going to go cuts and fills by material here. So we can see that, and if we add up these numbers, they're going to be, well, inherently different. And we can see that, well, for our fill through this section, let's go with 36.5 of our overburden, and we're using 53.2 of our solid rock. Now, in a practical approach, I don't know if I'd sit there with an excavator telling them to use this much of that for the fill. The big practical approach here is that we're just acknowledging that this is a mixture of material, and we're going to use whatever's cheapest. So he's going to take that and dump it over there and get his road, rather than assuming all of this is overburden. Last kind of talking point related to Opti haul. So this is kind of looking at that cross-section basis. If we have something more complicated and we want to see that material movement longitudinally to account for our different specific material requirements, we can. So Opti haul, copy Opti haul to clipboard. And we can take that and we can dump it over into Excel, and we can get that really, all the raw data, and we can look through it. The big difference, like the concept's the same as the mass haul. It's just instead of tracking it all as assumed to be one, we're tracking those cuts and fills by material and tracking where it's going in the mixture at those locations. So we dove down the rabbit hole, and I think that's it for me. Sorry for being so long-winded for a half-hour session.
Yes, we were going overtime, but we exceeded our overtime goal. So we apologize. We're gonna overschedule webinars in the future. With that, thanks for your patience. If you've got some questions, this is a great time. You can type them in that Q&A section of your GoToWebinar panel. Matt, we do have a couple here.
Okay.
To get us started. And yeah, if you need to jump off, I should tell our audience, you're welcome to jump off. If not, hanging tight, we're going to answer a couple questions. So our first question kind of goes back to this concept of report points. Do you have some recommendation for report points in really long road projects?
That is all this stuff, kind of the purpose of our presentation here today is more to show folks, or kind of show what's behind the veil, and hopefully give folks the knowledge to make the best decision for their specific projects. There's not really a one size fits all for any of this. Personally, for me, for a really long project, I'd be inclined to design it with whatever spacing was appropriate for a short project, and I'd break up my road into sections if needed. So our ceiling for what's practical to design in our software is longer than most. So yeah, that's I consider chopping it up into 40 or 50 kilometer chunks rather than dumbing down the spacing. One strategy could be, though, to do a high level pass with a sparser spacing and then add that higher density sampling in when you go to refine things.
Awesome. Okay, next question. This is my preamble, I should say, for it. We did some talk about volume calculations. All of this was in location. Our question asker is asking about volume calculations in terrain.
Oh, okay. Yeah, that's a good question. I won't go into it in detail just because I don't have a good example prepped. But yeah, in this, we're using a cross-section model. Terrain, you're using the tin, so you can subtract the two tin surfaces from one another to get the difference in between them. As far as a strategy, of course, yeah, part of this is just highlighting how it works so people can make sure they're comfortable with it too. But yeah, part of it is if you want to validate, does this make sense? You can take your road out of location and save it as a terrain file and do that tin subtraction in terrain. The two calculations shouldn't be exact. It's two different methods, but they should be reasonably close. And of course, if they're not, then that's an indication that maybe it's worth digging into what's happening.
Okay, let's take this one as our last question of the webinar, and thank you all again for staying with us and for so much overtime. Can you set a project to use Opti Haul by default?
Yeah, it'll just be setting up your screen layout. So view, well, if I wanted to constantly look at this with mass haul with Opti Haul in there, I'd hit save, and then the next time I open a project to work on something new, it would show me my mass haul diagram with the Opti Haul volumes. Same if you had have added in the full Opti Haul graphic. And then, yeah, the one thing I will kind of acknowledge is this optimization, this haul optimization isn't automatic. So in order to recalculate that, you have to do a recost. There are ways to set that recost to happen at every click, but that does slow things down a fair bit. So I would, yeah, I'd be inclined to roll with it conventionally and recost as needed.
Awesome. And with that, we're going to end 25 minutes overtime. Thank you so much, Matt, for taking everyone through all these key concepts. We hope you enjoy this presentation as much as we enjoyed creating it. The video will be up on our YouTube page. And if you have any other questions, feel free to contact us through our website. We're happy to answer any additional questions. With that, look forward to seeing you at an upcoming webinar. Thanks, everybody.
Thanks, everyone.